All right, let's jump right in. We are about to embark on a completely mind-bending journey, mapping out exactly how humanity's understanding of the cosmos has evolved over thousands of years. We're going from ancient philosophers staring at the night sky with just their naked eyes, all the way to modern physicists actually calculating the temperature of the universe seconds after its birth. It is a wild ride, so let's get into it. Now, to anchor our time-traveling narrative today, we're drawing entirely from some absolutely foundational source material. We're using Stephen Hawking's seminal work, The Theory of Everything. This incredible text is basically going to be our guide as we zoom way out from our tiny blue planet to the very edges of space and time. Here's the roadmap for this explainer. We're going to logically step through 6 major eras of understanding. First step, Earth at the center. Then, the sun takes over, followed by gravity and infinite space. After that, we hit the expanding universe, echoes of creation, and finally, we arrive at the Big Bang. Starting with part 1, Earth at the center. You know, it's super easy to look back and think early humans were just taking wild guesses about the stars. But actually, these early thinkers made brilliant leaps of logic based strictly on what they could observe at the time. What's really staggering, though, is the immense gap in time between these major paradigm shifts. I mean, we start way back in 340 BC with Aristotle. Then it takes centuries to get to Ptolemy's complete cosmological model in the 1st century AD. And incredibly, humanity basically just sat on that model for almost 1,500 years until Copernicus finally proposed a simpler, sun-centered model in 1514. Let's actually look a bit closer at how Aristotle deduced we lived on a spherical Earth, long before satellites were a thing. He just used relatable, everyday observations. First, he noticed that the Earth's shadow on the moon during an eclipse is always perfectly round. If the Earth were a flat disk, that shadow would be stretched out and elliptical, right? Second, travelers noticed the pole star appear lower in the sky in southern places like Egypt compared to northern places like Greece. Using just that, Aristotle even managed to estimate the Earth's circumference. And finally, a classic one, when a ship comes over the horizon, you always see the sails first and only later the hull. The Earth just had to be round. So the crucial thing here is how this progressed. Notice the massive contrast between Ptolemy's long-standing model and the revolutionary ideas of Copernicus and Kepler. Ptolemy had the Earth firmly at the center, and he used a highly complex system of spheres within spheres to explain how planets moved. But here's the kicker. It had a fatal flaw. To make his math work, Ptolemy's model required the moon to sometimes be twice as close to Earth as at other times, which means the moon would appear twice as big. People obviously knew that didn't happen, but they just kind of accepted it anyway. Copernicus and later Kepler fixed this whole mess by putting the sun at the center and realizing planets actually moved in simple elliptical orbits, not perfect circles. Which brings us to section 2, the sun takes over. The shift away from an Earth-centric universe wasn't just some math correction. It was sparked by a brand new piece of technology that forever changed how we looked at the sky, the telescope. Galileo had a massive aha moment in 1609. When he pointed his newly invented telescope at Jupiter, he literally saw tiny moons orbiting the giant planet. This was a total game changer because it proved definitively that not everything in the heavens orbited the Earth. Just like that, the Earth-centric model was completely shattered. Moving on to section 3, gravity and infinite space. Okay, so by 1687, we knew planets orbited the sun, but nobody knew exactly why. The mechanics of these elliptical orbits were finally explained by the discovery of a new fundamental force. Enter Sir Isaac Newton. His landmark work, the Principia, laid out the law of universal gravitation. Basically, every body attracts every other body. Newton actually noted that the idea of gravity came to him while he was in a contemplative mood, occasioned by watching a falling apple. He realized that the exact same force pulling that apple to the dirt was the exact same force keeping the planets locked in their elliptical orbits around the sun. But hold on, this realization created a massive problem. Think about it. If gravity is constantly attracting every star and planet toward every other star and planet, why hasn't the universe just collapsed in on itself into one giant ball? Newton's counter-argument was that the universe must be infinite, populated by an infinite number of stars. Because in an infinite universe, there is no central point for everything to fall into, since every point has an infinite number of stars pulling in all directions. Makes sense, right? Well, actually, no. That brings us to a fatal flaw in Newton's infinite static universe idea. It's known as Heinrich Olber's paradox. If the universe is infinite and static and has just been around forever, then no matter where you look in the night sky, your line of sight should eventually hit a star, which means the entire night sky should be blazing white hot, literally as bright as the sun. And even if you argued there were dust clouds absorbing that light, that dust would have eventually heated up and started glowing too. The only logical way the night sky could be dark is if the stars hadn't been shining forever. The universe had to have a beginning.
That leads us directly into section 4, the expanding universe.
Propelling us into the 20th century, our concept of the cosmos was about to zoom out exponentially, reaching far beyond the edges of our own Milky Way galaxy. To understand this leap, we really have to grasp the Doppler effect. You've definitely experienced this out on the street. When a car speeds toward you, its engine sounds really high-pitched because the sound waves are being compressed together. But as it passes and drives away, the pitch drops lower as the waves stretch out. Well, light behaves exactly the same way. We can measure the movement of light in the cosmos just by looking at how its waves are compressed or stretched. And Edwin Hubble used that exact effect to change the world in 1929. First, astronomers look at the color spectrum of a star and notice specific colors are missing. They're absorbed by chemicals in the star's atmosphere. Second, Hubble looked at distant galaxies and found those exact same missing colors, but they were all shifted toward the red end of the spectrum. Now, red light has a longer, stretched-out wavelength. Therefore, step 3, Hubble concluded these galaxies were moving rapidly away from us. The universe isn't static, it is actively expanding. To explain this expansion, Russian physicist Alexander Friedman made a massive, bold assumption that the universe looks identical in whichever direction we look and from wherever we look. He visualized the universe not as a flat grid, but more like the surface of a balloon with spots painted on it. As you blow up the balloon, every single spot moves apart from every other spot. There is no center of the expansion on the balloon's surface. Absolutely everything is just getting further away from everything else. Let's look at section 5, Echoes of Creation. Now, Friedman's idea that the universe is uniform everywhere was really just a mathematical assumption, until a completely lucky accident in New Jersey proved him right. In 1965, two scientists, Arno Penzias and Robert Wilson, were testing a highly sensitive microwave detector. But no matter what they did, they kept picking up this constant, really annoying static noise. It didn't matter if it was day or night or which direction they pointed the detector into space, the noise was identical everywhere. They soon realized they had unwittingly discovered the leftover radiation from the glowing, white-hot early stages of the universe. This constant background noise proved the universe was much denser and hotter in the past, which effectively killed the idea that the universe had just always existed in a steady state. And finally, section 6, the Big Bang. Prepare yourselves for the ultimate paradigm shift as we rewind the cosmic clock. If the universe is constantly expanding, like a balloon, what happens if we run the tape backward? If we rewind time 10 to 20 billion years, all those distant galaxies must get closer and closer and closer together. And if you go back far enough, you reach an exact moment where all matter, all neighboring galaxies must have had absolutely zero distance between them. This leads us straight to the hot Big Bang model. At the exact moment of the Big Bang, the universe was zero size, infinitely dense, and infinitely hot. Just 1 second later, it had expanded, but was still 10,000 million degrees, which is literally hotter than the center of our sun. Much later, as the expansion continued, the universe finally cooled enough to allow particles to clump together, eventually forming the stars, galaxies, and planets we actually observe today. To solidify this whole concept, in 1970, Roger Penrose and Stephen Hawking published a joint theorem. They provided the mathematical proof that, based on Einstein's general relativity and the matter we observe, there absolutely must have been a Big Bang singularity. They proved scientifically that time itself had a beginning, a precise point where all our known laws of physics completely break down. Which leaves us with this final, profound question to end our explainer. If the very laws of science break down at the Big Bang's origin point, are our lives and our universe completely predetermined by that initial explosive state? Or, because predictability fundamentally breaks down at that singularity, is there a hard limit to what humanity can ever foresee? I'll leave you to ponder your own place in this massive, evolving cosmos. Thanks so much for joining me on this incredible journey.